Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be talking about the Fibonacci sequence. This is a pretty famous sequence. A lot of you know that this sequence starts with the numbers 1 and 1, and then every number from there is always going to be equal the sum of the previous two terms. So if we put the 1 and the 1 together, we get 2. Then if we put the 1 and the 2 together, we get 3. And then we continue in this manner. 2 and 3 gives us 5. 3 and 5 gives us 8. 5 and 8 gives us 13, right? Then we would have 21, etc. from there, right? So we always take two terms, add them up to give the next term in the sequence in that case. The numbers start growing kind of slowly, but this is going to ramp up and the numbers will get pretty big pretty fast from here as well. Now, one thing that's definitely good to review with the Fibonacci sequence is other ways of describing. So the main way you will see this described is with what's called a recursive formula. So the recursive formula for any sequence, or in this case the Fibonacci sequence, has two parts again. First of all, you have to tell where we're starting. What are the initial conditions? What is the kind of beginning point? So the first two terms, f1 and f2, are both 1. And then from there, you have your recursive formula. You have the next term, or fn, depends on the previous two terms. So this depends on fn minus 1 and fn minus 2. So these are the two components we have if we're talking about our recursive formula. It's the same definition as before, but it's good to kind of practice seeing it and written out a little bit here with this recursive formula as well. Now, let's look at a cool example and kind of an application of the Fibonacci sequence. There are many identities with the Fibonacci numbers. They have some cool relationships to other numbers you may know, right? Pascal's triangle, all kinds of cool things that I definitely recommend you look into. The one identity we're going to talk about right now is what I'm going to call this squares identity. If you add up all the squares of the first however many Fibonacci numbers, you actually get that Fibonacci number times the next one as your result. So as an example of this, let's look at, right, the case where n is equal to 5. So suppose you add up the first 5 Fibonacci numbers, which we know from before are 1, 1, 2, 3, 5. And then when you add up those things, you should get the 5th Fibonacci number times the 6th Fibonacci number, which is 5 times 8 in this scenario. Now, we can check this algebraically, right? That's pretty easy to do. 1 plus 1 plus 4 plus 9 plus 25. You will get 40, which is 5 times 8. But that doesn't help you understand why this is true or the pattern or anything there as well. So actually, the cool thing you can do with this is think about this 5 times 8 as a rectangle. So let's draw out a 5 by 8 rectangle in this case, right? So I have my two dimensions here. We have 5 and 8 in this rectangle here. And now, right, every square can be thought of as a geometric square, right? So this squares has a couple of meanings here. One, we have the meaning as kind of the obvious definition of, okay, we're squaring the different numbers. But we can also think about this as actual geometric squares in this case. So for example, when we see this 5 squared here, right? So we have 5 squared right here. We can actually interpret that as a 5 by 5 square in our rectangle. right? So I'm not going to label all of these, but for the first one at least, this is our F5 squared in this case. We have a 5 by 5 rectangle there. And I think you can see where we're going with this from here, right? We can now take our 3 by 3 square out of this, and we can take a 2 by 2 square out of this, etc. And then we're kind of left with our two 1 by 1 squares as well on the bottom. And right, you can do this in different ways, and if you kind of do this in a nice pattern, you can actually see how this could be continued as well, right? So if we wanted to add another square to this, an 8 by 8 square, this is going to kind of mess up the screen a second, right? But we could put a big 8 by 8 square up here, right? And this is how you would kind of continue in these squares added. And this is not only the example we did for this one problem, but you can kind of see how this works in general. So here we have our F4 squared, etc. So you can keep adding these bigger and bigger squares and build a bigger and bigger rectangle and have this nice relationship for the Fibonacci numbers and the Fibonacci sequence. That'll be a good place to stop for today then. So check back each Thursday for a new math tidbit in 2021. And I hope to see you guys on the ZIML site for daily math practice and other resources as well. Goodbye.